Good afternoon. This is David Eastwood, Geotech Engineering and Testing. Thank you for attending this webinar on geoforensic study of a detention pond segmented block wall failure in Texas. I hope everybody can hear me. Let's see, I got one question right here. I can hear you. Okay. Audience, we got about 220 people RSVP'd here. We got a lot of civil engineers. We got architects, a lot of people from various cities, structural engineers attending the webinar. Yeah, that's good. Of course, my name is David Eastwood. My email is de@geotecheng.com. If you need to reach me, my number is 713-699-4000. Just kind of tell you this presentation is going to be on YouTube. You're not going to learn everything right in the first round of this thing here. There's a lot of information, so you may have to go back and watch this on YouTube again. This be a good reference document. Geotech Engineering and Testing is located in Houston. We work all over Texas, Louisiana, New Mexico, and Oklahoma. And we have been around for about 38 years. We do geotechnical, environmental, material testing, and geoforensic engineering. That's about 10% of our work is forensics. And we have a staff of about 60 engineers, a lot of masters and PhD guys, and work all over Texas, Louisiana, New Mexico, and Oklahoma. And we have all rigs, so we can mobilize on jobs quickly. Got another message here. Okay, good. If you have any questions during the presentation, please click on the Q&A on your screen. I've got a cold, so please bear with me. What we're going to be talking about today, we're going to talk about SRWs, which is segmental retaining walls, introduction, project timeline, site visits, field exploration, laboratory testing, engineering analysis, causes of foundation, bulkhead failure, block wall failure, and our repair technique. As part of our presentation, we're going to talk about a little bit about concrete block walls, what they are, because some people may not know what the block walls are. Basically, block walls are constructed as small blocks that have surface area approximately 1 square foot. The reinforcements are usually with plastic geogrids, although fabric and metallic reinforcement have been used. The reinforcements are laid between the courses of the blocks and depend on friction between the blocks and mechanical device for anchorage. These walls are usually built on a batter, which is usually 1:6 or to 1:48. So they're great systems. They're relatively cheap systems, cheaper than any other kind of retaining wall. And they've been around for a long time. They use them a lot for detention ponds. And the walls that are detention ponds are kind of different than block walls with detention pond, different than regular block wall systems. You got to design them a little bit differently. These are some pictures of the block wall systems that are used for detention ponds. Yeah, this one is near Woodlands, by the way. I always remember that one. There's another one right here. So they got them all over the place now. They're very good. They last a long time, and they're easy to build. They're economical. The way they have them all basically set up is they got the wall units, and let's see if you can get. This is the wall unit in here. You got the drainage chimney here. This is the soil, natural soil. This is the leveling pad, can be either lean concrete or it can be gravel. And a lot of people just use gravel. Topsoil. And the way they make them, they mixed sand and gravel and cement. They run them through an oven and dry them up and cure them. Not that very high temperatures, just you know, room temperature type stuff. That's what it looks like. Okay, the way the way they work is the facing units, proprietary product interlock systems. Basically, they have friction. And, well, they got lips in here. They got pins. Got clips, friction, molded flanges. That's how they kind of do a load transfer to each other. So a lot of times it's friction by itself. And the geogrid goes right there in the middle of it, kind of like that. Typically a frictional connection. Unique connection curve block each grid repair. But essentially that's what they are. It's all friction. So this is the old basically a block wall system in Middle East. It's been there for many, many years. This is the wall of China. That's a block wall. So it goes back block wall systems many, many years. They're very lasting if they're built right and designed properly. And they use a lot of geosynthetic soil reinforcement, a geogrid or geotextile. And of course, the geogrid there or geotextile, it's always in tension. So basically, it holds the soils behind the block walls in place, and the geogrid is in tension. Block wall construction, the way you put them in the ground is you basically you put a gravel pad in, make sure you compact it, or you put lean concrete and you start lining up your block systems, make sure they're level. If you need a drainage layer, you put the pipe behind it, the drainage pipe. So that's how I start putting them, stacking them together in a batter. This is the geogrid itself. Again, this is in tension. It's placed between the block systems. And you have to compact that soil behind it. And I'm going to repeat this many times because that's where I see a lot of the failures happening is the backfill they use behind the walls are not good. You cannot use clay or lean clay or fat clay as backfill behind these walls. You got to use sand, gravel, things like that, but not clay soils, not silt, sand or gravel. And again, I'm going to repeat that many times because I see a lot of these walls are going in and people are putting lean clay behind as backfill in between the geogrid segments. Here you go, they're lining them up. Again, you can see that they run gravel through the block walls. Okay, somebody asked me, says, why can't you use clay backfill? I'm going to answer that as we go through it, but the clay soil's got low angle of internal friction, so they provide very little friction. So these walls they cannot be designed safely with clay soils because of low friction angles. In soils, like in clay, they got short-term properties, long-term properties, and rapid drawdown properties. 3 separate soil friction angles. 0 and short term for short term, long term, and you're gonna have another fee, and the rapid drawdown, you're gonna have another fee. So don't use clay for backfill. You can't. Low fee angle. Okay, so we got it over here. You can see the fabric in here. You got the gravel pad. Again, you see your blocks filled up with gravel. This is the fabric going behind it. You see that? This is the geogrid. Just line them up behind the wall. You can see the system in here, the drainage layer. This is the block wall. Got a question here. How far is the vertical spacing of the geogrid, and how far back does they have to go to develop tension? Okay, I'm gonna get to that, man. You guys are ahead of me here. Give me a few minutes when I get to it, and then we're gonna get into it and discuss that. Anyway, this is the geogrid. It's basically you run internal stability analysis on it, and there's a software you use, and based on that, you determine the type of geogrid and amount of tension they can take. But I'll talk about that in a minute. Again, you see the geogrid here behind the wall. So when you put these walls in, you got to do an excavation behind it so that you can put the backfill in and the geogrid. So you remove a lot of the on-site material, especially if they're sand, if they're clay and silt, you're gonna have to take them out. The block wall, the geogrid, block wall, geogrid, drainage pipe if you need to. Okay, so when you do block wall design, you should design it in accordance with National Concrete Masonry Association manual. This is the latest one that I found on the internet. It's a very good book. You got to be careful how to use it. He's got some stuff in there with respect to soils. That's not very accurate. So I'm going to talk about that as I go through this, that if you use this design manual, you're going to have to use your soils engineer to help you with it, because some of the parameters they give you here are not accurate. So if you got a short block wall, 3-4 foot tall, you can just put gravel behind it with no geogrid. And there are some design charts right here from Anchor. And if you look at them here, he just says put in, some gravel backfill behind these things or sand. This is a flat top here with basically no slopes, no surcharge. You can put the block walls in there and put some gravel behind it. One thing that I don't agree with the Anchor chart is it says clay and silt feet 26. Okay, that's not accurate. So I think for clayey sand, feet of 30, if you got not even clayey sand. For sand, feet of 30 is good. Clean sand, feet 34 is good. But I wouldn't be using clayey sand. I wouldn't be using just clay and silt. These parameters are unconservative that they're given in these charts. Here's another one by Anchor. You got clay feet of 26. That's way too high. And you got silty clay feet of 30, too high. And then, again, you put some gravel in there. Once you get above 10 foot, it says you have to use the engineer wall design performed by a professional engineer. And that's when you have 250 PSI surcharge on it. If you go with sloping, again, they got the same concept. Again, I don't agree with their soil parameters. Here, they just you got to use sand and gravel in the back. Do not use clay. And use the backfills in here, and you can see a slope like this. Again, here, you got to use an engineer to design it. But for like a 8-foot wall, you can put gravel behind it. Now, if you start going higher, taller walls, you got to put geogrid reinforcement in it. And you got a drainage collection pipe at the bottom in here. This is the natural soils. You excavate behind the wall. You take out all the on-site clay soils or sandy clay soils or silt. You take all that up and put gravel and good sand, SM sand behind it. I got some gradation for you in the presentation in terms of the backfill. Backfill is really important, very important. This is by Anchor again. When you use GeoGrid, no slopes, no surcharge. And here's the kinds that you need. You can put, GeoGrid in them. Here you start above 12 foot. He says use the engineer. I would use engineer anything above, 3-4 foot. And 3-to-1 slope in here. If you got a sloping backfield, again, wrong soil parameters here. GeoGrid, and it says above 10 foot with a sloping. Use engineers for clay soils. Fee angle for clays. When you use these things, fee angle for clays, you use what's called residual soil strength. That's when the soil has already kind of essentially gone through the peak value and is at higher strain levels, soil strength. And so let's say you got a typical Houston soil, a PI of 50. That means your fee angle is 15. The manual lowest value that they give you is in there is 24. So that's where the screw up can come in. So it's very important to use proper soil parameters for these things so that you don't have wall failures. Use residual soil strength when you coming up with the strength for the for these wall backfill. Typical base of it, when you put the block walls on the ground, you put some gravel underneath it. This gravel should have a basically gradation like this: 100% passing number 1 inch, 35 to 75% pass number 4, 10 to 35% pass number 40, and 3 to 10% pass number 200. Base of the gravel should be minimum of 6 inches, or you can have lean concrete as a base material. Now the backfill, drainage layer, drainage aggregate behind the wall should have basically 100% passing number 1 inch, 75 to 100% pass 3/4 of an inch, 0 to 60, number 4, 0 to 50, number 40, 0 to 5, number 200. Now reinforcing fill, it says use gravel type material or SM, which is sand. Okay, so gradation 1 inch, 100% passing. Number 4, 2 to 100% passing. Number 40, 0 to 60% passing. Number 200, 0 to 35%. Okay, so you can use ML, which is silt, CH, fat clay, OH, organic clays. You cannot use any of that stuff. You cannot use sandy clay or clayey sand. So CL, you cannot use lean clay. Make sure you use sand and gravel for backfill. You got to design these walls for overturning, bearing capacity, settlement, bearing capacity, global stability. That's a big deal. Structural engineers cannot do global stability. And they don't ask geotechs for global stability. But it should be in the scope of the work for the geotech to do global stability for your wall. Okay, and that's not cheap. So you got to do it right. Overturning, settlement, drainage, and sliding. So you got to design for these items in here. When you look at the manual, all they ask for is bearing capacity, essentially. You got to do the global stability, and the structural guy cannot do it. You got to get the geotech to do it. Advantage of block walls. Performance, design flexibility, face drainage. Face drainage is questionable. I'm going to talk about that in a minute. Ease and right of the insulation, economics, durability, ecological friendly. Performance, dry stack system, tolerate movements. So if you moves a couple of inches, it doesn't hurt anything. SR units may move and adjust relative to each other. That's good, it can move. Design flexibility, site designer, flexibility with respect to retaining wall location, wall layout, height, constructability, typical small size, and weight of the SRW units that can be moved by a person. Face drainage, theoretically, if you have gravel backfill behind these walls, or good clean sand, they got good drainage. But if you put clay behind it, they got poor drainage. And so this drainage supposedly is supposed to reduce the hydrostatic pressure behind the wall. If you put clay backfill, you could potentially have hydrostatic pressure behind the wall, and the wall is not draining properly. Ease and rate of insulation, they're fast. You can put it together real quick. And an experienced crew can put about 300 to 500 square foot of the wall per day. Economical, cost 25 to 40% cost advantage over cast in place concrete retaining walls. Durability, they last 75 to 100 years. Oh, so this was our project site in here. This is the building. They have the detention pond for the property right in here. This is located in Montgomery County, Texas, Highway 105. And the wall was 17 foot, the detention pond was 17 foot deep. And the design was supposed to use tensor, but they use basically Mirify instead, which was we had this specific product had lower tension capacity. Okay, I got a question in here. What are the concerns about building homes on top of the backfill behind the walls? Number one, you cannot build a house on top of the backfill of the block wall system. I wouldn't put a house on top of it in general, because I don't want that foundation system, the grade beams penetrate the geogrids. If they cut the geogrid or something like that, you can put them just outside of it. And when you do that, as part of the design, you got to do global stability, model the house out there behind the wall and run global stability, make sure that surcharge load for a typical 2-story house, you put somewhere about 400 PSF loading and run it, and make sure that thing is not going to cause global failure. But the geotech needs to be doing that. A lot of times geotechs have no idea something like that is going on. They don't tell us anything like that. Okay, when they were designing the wall in this case, they used a phi of 28 degrees for clay soils behind the wall. 28 degrees, it's way too high. Okay, somebody asking me, it says, are all walls filled? I don't know what the question is. If you're talking about the block wall, inside the block walls are filled. Behind the walls got to be filled with this, with gravel or sand. If that's, hopefully I'm answering you. You got to be more descriptive. Tell me what you were asking me. So this guy's used 28 degrees for clay. Okay, that's number one. You can't do that. Another question. You answered it. Okay. And when you look at this thing here, in terms of soil type, again, phi of 28 degrees. Let's go to the next slide. Okay, the wall was from elevation 212 to elevation 195, roughly about 17 foot tall. And they had 9 layers of geogrid behind it. 9 layers. And the geogrid was tensor as it was designed, okay? Another question. Is it okay when the house or a building is outside the 1-to-1 ratio, outside the retaining wall heel? Yeah, you can put it in as long as it's not in the backfill of the not MSC block wall system. That goes with the MSC wall as well. Don't put it in the house on top of the backfill of the block wall system, and it has to be modeled for global stability by the geotechnical engineer, which most of the time has nobody tells them anything. So it has to be modeled and checked for that. For a 1-story house, you put a pressure behind the wall of roughly about 250 PSF. For 2-story house, you put 400 PSF. Okay, another question. Would the gravel backing migrate the migration of a pond volume out versus clay backfill? Yeah, but these are detention ponds. I really don't care if the water comes out of the detention pond and goes to the surrounding soils. Remember, there's a gravel behind it, and behind the gravel is clay. So it stops at that level. So typically it's not a problem if the water is seeping out the pond. But in general, if you have clay behind the wall, behind the gravel, it's not going to seep out. Pictures of the wall construction. And you can see the block wall system in here. You got gravel draining, behind it, inside the blocks. They got the geogrid going behind it. It's a mirified geogrid. Okay, another question. Do reinforcement calculations accounts for deflection to go around utility and structural conflicts? I'm sure it does. There's a good software that I'm going to talk about in a minute that you can use. You got to read the manual, see how they account for that. I don't essentially don't do the structural design for those things, for these. So the manual answers a lot of the questions. So you see the geogrid going behind the wall in here. You see the geogrid between the block wall systems? Yeah, you got gravel behind here, in here, and just right behind the wall. The excavator is 16 foot wide behind the wall. The geogrid design link was 12 foot. Again, 16-foot excavation, 12-foot geogrid. You can see the geogrid right in here. Again, I would put the geogrid between all the wall, all the way up to the front. It's really. And you can see wall is coming up. The backfill behind the wall is sandy clay. They put some a wire mesh behind on the bottom of the pond, and they pour concrete and put some concrete bottom pond. Here's the geogrid. They put pump concrete on the bottom of the pond. Got another question. I see equipment almost among cities that a retaining wall taller than 4 foot needs to be designed by a P engineer. Why is that the case? Because you don't want the wall to fail. You're gonna have to use proper engineering. So it's a good idea if wall above 4 foot be designed by engineer experienced in designing of the block wall system, if it's a block wall. Remember San Antonio, they had a block wall system that failed and many homeowners had to be removed. A lot of people suffered. And you can see the inlet in here, pipe going here towards into the block wall system. Again, you see the geogrid as the wall is coming up. The backfill is sandy clay. It's a completed wall. Detention wall design was 2021. They used Keystone system. June 28th, site plan drawings, design of height of wall 17 feet. April, the wall had failed, so we had to go out there and look at it, see what's going on. Okay, question, is there a recommended maximum slope behind the wall? Typically behind the wall, I like to have slopes at least 3-to-1 slopes. If it's steeper than that, you got to run slope stability. If it's gravel, it will stand up, but if it's clay or something, it's going to fail. Site visits. We went out there, look at the detention pond. These are some observation points. We'll look at it. If you look at the fence on this around the pond, it's all busted up. It's all tilted. Lots of erosion around the pond. The wall failed at the bottom in here. These are where the inlet is coming in. The walls will start bowing. More inlet. That's an inlet outside the detention pond. Here's the fence. A lot of erosion. Got some dispersive soil here. You see the wall bowing in here. Another picture of the bowing of the walls. Failure in the bottom. So we went out there, did some investigation. We did soil borings and ground penetrating radar, GPR, and we did some test pit excavation to see how it was constructed. Question, we got some couple questions. What was the slope failure behind the bottom of the retaining wall? Global failure. That's what happened with the bottom behind the wall. Global failure. Okay, another question. The retaining wall in San Antonio that failed was called river mist. That's right. It was a block wall system that failed. Okay, here's another question. Would you ever recommend a stone gravity wall over this staggered block wall geogrid configuration? That's parameters would be driving decision between two. What alternation required to your design if the client wants to use expensive on-site backfill? Number one, gravity walls are more expensive than a block wall system with geogrid. Block wall system is a gravity wall too, and but it's got geogrid in it. You don't have to use as much mass on it than regular gravity wall. A lot of people are not going with gravity walls anymore. Everybody's going with block wall system. And if somebody wants to use expansive soils as a backfill material, you don't put your stamp on it. It's not acceptable. You're going to get yourself in litigation. Okay, so soil investigation. These are the test pit locations. The blue, the red one is the borings. We did one boring on each side of the walls through the geogrid. The borings were 35-foot deep with the GPRs, up to 12 feet away from the detention pond. And we did 4 test pits around the detention pond to see if you can see the geogrids. We also ran density tests. This is our drill rig over there, doing borings around the detention pond. So, did 4 borings. This is sandy clay material. You can see the sandy clay material behind the backfill. This was fat clay here. Fat clay, sandy clay. Checked its strength of that backfill with the hand penetrometer. We also did GPRs. It just uses electromagnetic energy, like a cell phone. That's what it looks like. Looks like a lawnmower. It basically determines high areas of high moisture and voids behind the wall. Here's the guy who's running the GPR at various locations around the pond. We also did test pits, 4 test pits, and each test pit had 2 holes in it. We went all the way to 12 feet away from the wall to make sure the geogrids were there. We measured the distance of 12 feet with one right next to the test pit next to the wall and one away from the wall at 12 feet. Two sets of test pits at each locations. And this is a test pit next to the wall, test pit away from the wall. We found the geogrids in the bottom of the excavations. Some more geogrid. Some more geogrid. You can see them. Geogrid. 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 Some of the holes got filled with water as we excavated them. It's called perched water table. Geogrid. Geogrid. So we measured the width and the length of each test pit section. Ran a hand penetrometer to make sure to see what kind of soil strength we have in the backfill, how strong your backfill is. Measure the dimensions, depths, check the strengths, sizes. Got 2 questions. Somebody says the voice is not good. Can everybody hear me? If not, let me know. I don't know what's going on, but I haven't heard that complaint. Okay, everybody else hears me. Maybe there's a problem with the system. You got. Is a block wall with a pin system more stable than the block wall with no pins? I don't think so. I think they're just both fine. Another question. Can hear you just fine. Okay, I can hear you okay. Voice is okay. So most people can hear me fine. Okay. Test pit number 1. If you look at test pit number 1, you have 0 to 16 feet. You got lean clays, sandy clay. And basically excavated it. The width of it was 20 inches. The length was 28 inches. Depth was 16 inches. The soil was 0.15, very soft soil backfill. 0.15 TS, so that's 300 PSF strength. Length of fabric was 12 feet. Okay. Test pit number 2, 0 to 20 inch was lean clay. Soils were soft. No water in the hole. The fabric was 12 foot long. We also did the nuclear gauge. The nuclear gauge measurement for density. It's got a nuclear source in here, emits gamma ray. It's got receivers in here. The more of these gamma rays hit the receiver, the looser your soil is. The less that they hit it, the stronger the more dense your soil is. It's called a nuclear gauge system. We ran density at the top and 12 inches down and 24 inches down. To see what the density of the backfill soil is behind the wall. So we ran a bunch of density tests. Laboratory tests, we got samples of the soils. We done classification tests, strength tests, Proctor tests, moisture content, Atterberg limit tests, hand penetrometer, unconfined compression, 12 rain, Proctor tests, determine degree of compaction. We found boring B1, B2, B3, B4. We're up to a depth of 16 feet or so. We had sandy clay. Below that, we had fat clay. Sandy clay had a phi of 22 degrees. Fat clay had a phi of 15 degrees. So we had 0 to 14 lean clay, then 14 to 19 lean clay. In some areas, 14 to 35 fat clays. Soil PIs in the lean clay was 15 to 30. Fat clay was 32 to 34. With lean clay 20. Fat clay 32 to 45. So they had some bad soils backfill. You look at this thing in here, the strength values are very low. All the way down, very low strength. It ran the densities. In this case here, most of the densities passed. Okay. The PIs are 20, 19, 22, 24, 32. That's boring B1. Boring B2, low densities. Some of the densities failed. Low strength, some of the densities fail. PI 16, 29, 19, 34. Okay, B3, very low strength. Densities fail at the top, but the rest of it pass. That's B4, low strength all the way down. Densities pass, PIs 32, 19, 15, 19, 20. Basically, sandy clay, we call it lean clay. So, on-site field compaction, the PI of the soils was 15 to 34. Dry densities of 104 to 107. Optimal moisture was 16.5 to 19. Degree of compaction of the soils, 44 to 100%. Degree of compaction should be 95% standard Proctor density. Did not pass compaction. These are the Proctor tests we ran. Liquid limit 48. Plasticity 18, PI of 30. This one's got 55, 20, and 35. This is the summary. Test pit 1, densities failed. Test pit 2, failed. All of them essentially, these densities with the nuclear gauge, they failed. Engineering analysis. We looked at aerial photos to see what was out there. We looked at topographic maps. And the pond flooded. We checked the quality control. We checked the compaction. We looked for perch water table. We look at the soil shear strength. And we look at the soil moisture profile. We look at the PVR, potential vertical rise. We look at the GPR results. We look at the bearing capacity of the soils. We look at block wall failure analysis and global stability. This is the site in 1995, was wooded site. Question, was there a QC/QA conducted during the construction for comparison? There was very limited QC/QA done. Very limited. That's on typical projects. Most projects don't have much QC/QA. And you can see that in here. There's a few trees out there on the site. 2006, 2011, 2017, 2022. You can see the site's cleared. They start digging the detention pond. This is a topo map of the site, relatively flat. During the construction, detention pond flooded after the construction. That's a big deal for detention ponds. When you got a clay backfill, when it gets flooded, the clay soils will hold the water in the soil itself. So essentially the soil is saturated, it's got low effective stress. That's where you're going to get a global stability failure. The pond was full of water. Water was removed, but the backfill was still saturated. This is a detention pond that flooded during the rainfall. I don't know what kind of a detention pond is that gets flooded. Not supposed to. You can see the water everywhere. Quality control. According to the design manual, there should be quality control during the construction. Geotechnical engineer should conduct geotechnical borings, get the soils data, give all the information for design of the block wall system. If asked, conduct global stability analysis. We usually not asked to do global stability analysis, and the structural guy is not qualified to do global analysis. We need to define basically the subsurface conditions, determine properties of the strengths of the retained soils, evaluation of the bearing capacity of the soils. In this case, this was not done. There was no borings done for this detention pond. They just dug a hole and started putting the blocks in. Quality control, engineer suggested roles. Structural engineer should look at the external stability, sliding, overturning, internal stability, facial stability, determination of the maximum unreinforced height, design of the geogrid system, determination of the minimum embedments of the wall. If there is any scour, specifications and approval of the wall units, determination of what structures can be placed within the reinforced zone of the wall. That's a big deal. If you want to put something within the zone of the reinforced, it should not penetrate the geogrids, and it should be considered as part of the modeling when you do global stability. Again, we don't know these things when we design these things at the beginning. It's for geotechs. Quality assurance continued. If contacted and notified, construction observations can be conducted. When required by law, SRW engineer must be licensed professional engineer, which we recommend that to be the case. During the construction observations, all the earthwork need to run density tests on all the backfill. Check the soil to see the backfill is sand and gravel and not fat clays and lean clays. All the geogrids, make sure they are spread properly and they're placed behind the blocks. Inspection of the native soils in the retained zone. Monitoring of the field placement, density testing, overall material installation and inspection. Construction observation wall unit and geogrid installation, review of the material submittals if there is, for conformance with the specifications, additional soil properties, earthwork testing. You know, for this specific project, very minimal quality assurance was done. Freshwater table, some of the holes we excavated behind the wall, they had some water coming in. That means water is trapped in the soil behind the wall. That means the hydrostatic pressure is not relieved. Okay, so you have to assume the hydrostatic pressure when you do the wall design. Shear strength, we ran the soil shear strength on this project, and the lean clay soil backfill had a phi of 22 degrees. Very soft soils, but phi of 22 degrees for design purposes. The design manual doesn't have anything less than 24 degrees in it. Moisture profile, if you look at the borings we did, this is boring B1. The red one is the in situ moisture. The green one is moisture at wet condition when the soil gets wet. And the blue one is when the moisture is dry. And the soil was at an average moisture condition all the way down. It was not real wet and it was not real dry. Again, the B2 was the same average moisture conditions. Not very dry, not very wet. B3, the soils were dry. The red area is below the dry line. It was kind of a dry soil out there. And B4 was wet above the green area. So it was a wet soil condition there. PVR, potential vertical rise, is a property of a soil that shows how much heave you can experience at a specific location. The soils over here were lean clay, so the PVR was low, was 1.4 inches, which is adequate. That's fine. The results of the GPR. Okay, somebody's asking a question. Was there determination of that what caused the local bottom block wall failure pop out? Yeah, give me a minute. We'll try to get to causation in a minute. Ground penetrating radar. We ran the GPR test, indicates potential voids in moisture conditions at the project side. The blue area is a high moisture. These are the high moisture areas behind the wall, and the red areas is potential voids. So there were some voids, small voids out there. Well, not real small, some voids out there in the backfill behind the walls, according to GPR. That's the kind of shows anomaly out of here with GPR behind the backfill, in the backfield behind the wall. Bearing capacity, we ran the number here. We had a bearing capacity of 1500 PSF. Block wall failure analysis was analyzed. There's a key wall program that the manufacturer provides, and you can design the walls based on that, based on the block wall system. And again, GeoGrid Mirify was used instead of Tensar as backfill, as a GeoGrid behind the walls with lower tensile strengths. The design manual used the friction angle of 24 degrees. That's the lowest it allows. This job had a phi of 22 degrees that the program did not allow for. So there's got to be maybe a modification to the program to allow for lower phi angle in the modeling. When you run the wall program, you will see the base sliding pass, bearing capacity pass. You got factors of safety here. Crest topping failed. Internal sliding failed. Pull out failed. So these are some of the tests, some of the stuff from the program that shows maximum reinforcement separation fail. Maximum multiple facing height at the top, RS failed. Segment of the wall was not properly designed in this case. L is reinforcement length, which was 12 feet. H is the height of the wall here, by the way, 17 feet. Global stability. That's the big deal what we did. We ran the global stability assuming a rapid drawdown conditions where the detention pond got flooded. They pumped the water out of the detention pond, but the soil behind it was still saturated. So there was hydrostatic pressure behind the wall. So if you use that and use a phi angle of 22 degrees, we analyzed it for short-term, long-term, and rapid drawdown. Short-term parameters represent end of construction. Rapid drawdown represents water level change condition. Long-term conditions applicable to soil gravity loads continuously applied live loads. Steady state conditions. Global stability, short-term was fine. We ran the short-term, there was no problem with it. The soil parameters that we used, 0 to 20 feet, we had lean clay, we had phi of 22 degrees. Below 20 feet, we had fat clay, phi of 15 degrees. All this should be modeled. The structural engineer is not going to do this. You should get the geotechnical engineer to run the global stability. These are the modeling of the stability. We had the lean clay backfield. This is the pond. This is the fat clay. Here's the slope failure. Factor of safety of 1.4. Global stability for rapid drawdown, 0.5, not acceptable. For rapid drawdown, for long-term, factor of safety of 1.2. So short-term was 1.4. Allow was 1.3 factor of safety. Rapid drawdown 0.55. Acceptable factor of safety is 1.25. Long-term 1.2. And the required factor of safety is 1.5. So the wall was essentially unsafe. So based on the evaluation of the field and laboratory excavation, laboratory field exploration, and laboratory testing. Basically, the wall fell as a combination of inadequate design, improper construction, and improper backfill materials. Inadequate design. No soil investigation was done to design this wall. National Concrete Masonry Association indicates the soil parameters for the wall should be provided by the geotechnical engineer. There was no geotech. Phi angle of 28 degrees used in the design. It should have been 22 degrees. And for the soils below 20 feet, it should have been 15 degrees. The results of global stability analysis that the wall is not stable. No specific drainage system was designed behind the wall. Construction, based on the field review of the pictures during the construction, did not meet the design. They didn't follow the design recommendations for construction. The degree of compaction behind the wall was not 95%. And the GPR showed presence of voids and high moisture. There was hardly any quality control was done with the backfill behind the walls. Inadequate material. The geogrid they used was a Mirify, lower grade. It had a tensile strength of 2909. Well, actually, the shear capacity of the block wall that they used was 2909, and it was designed was 5,058 pound-foot. So the shear capacity for the block walls were lower. They didn't use the exact design block wall. So these are the block wall here, and it was designed for 5,086 in the design, but they used 2909 shears, maximum shear capacity. The maximum shear reinforcement, the geogrid that they used was Mirify. The tensile was 2781. The design was 4709. So they changed that. So the tensile they had to use, the design was 4709. They used 2781 for their tensile strength. Summary. Based on the documents reviewed, basically, the failure occurred as a result of no soil investigation done, improper soil parameters used for design, no block wall drainage was provided, construction was built not as per the design, construction defect, field soils were not properly compacted, construction defect, presence of voids around the detention pond, construction defect, detailed quality control was not done, construction defect. No shear strength block wall system, material defect. No shear reinforcement, material defect. We recommended the existing detention pond be removed, be replaced with a whole new one. So that's what they did. Actually, they tore it down and built a new one. And they designed it right this time. So that's the end of the presentation. If you got pictures of the projects, please send them to me. I use these pictures for training purposes. I appreciate if you send me the pictures. This presentation is going to be on YouTube, and you can go watch it again. I don't expect you to catch it all at one time. There's a polling on this thing here. I don't know if it works or not, but let's see if there's a poll here. I don't see a poll. There we go. Yeah, I got the poll going. Hopefully you're gonna get it. If not, you can't get it, then tell me what you think of the program. If you need to reach me, my email is de@geoteching.com, 713-699-4000. We have a bunch of upcoming webinars coming up, so you're gonna be on our lists. So you're gonna get the emails with some of these training programs. We're gonna CD and send you the PDH in about a week or so. Questions? Okay, question here. How should the wall be properly designed for rapid drawdown? As part of the design, Geotech needs to run the rapid drawdown case for the structural engineer. Once all the information is available for detention pond, you need to run that case depending on the backfill on the behind the wall. If the backfill is gravel The rapid drawdown may not be a big deal, but if it's fat clay or lean clay, it's going to be a problem. Next question. Thanks, David. Good presentation. Okay. Could you put up your contact information again? Yes. Let me see. I can go back, get the contact information. Uh-oh. Let's see, the share window is closed. Let me share it again. Okay. Okay, we got it all the way at the bottom, beginning, but here's my contact information. Let's go to the question again. Very informative, thanks, good, and here we go. Question, were there options considered in migration remediation rather than complete replacement? No, we did not look at any other mitigation. It would cost too much money and takes too much time. We just felt like it was better to just tear it down and build a new one. Ron Bavarian, thanks, David. Good information. Well, I'm glad you like it. Thank you. Great info. In your opinion, was the material or construction the major factor in the failure? I think there was I would say 30% design, 30% construction, and 30% wrong materials. Essentially, if you want to go about it, it's probably 30% design, 70% construction. Is there a drain pipe needed if gravel is used? I don't know off the top of my head. I would say yes. We wanted to get that water away from the behind the wall, so that's the only way you get it out would be with a drain pipe. Very interesting. Thank you. I email you with an interesting story. Send me pictures. Thank you. How long does it take for a wall to fail? As an example, the wall failed as soon as the construction was over. So it took them about, I don't know, a month or two to build it. So it failed right after that. Any other question? Well, I appreciate everybody's time. Please call us if you have any questions. Contact me if you got geotechnical reports you want it done. If you need soils investigation or forensic studies.